Okay, hello everyone. This is tutorial 1, which is actually a review of the material studied in the previous course of linear algebra. My intention is to discuss 3 topics with you today. The first topic will be the solving of systems of linear equations by Gaussian elimination method. So Gaussian elimination method. This has been the first and the biggest topic today. The second topic is linear dependence or independence of vectors. Linear independence, dependence of vectors. And the third topic, if he has some time left, will concern the question as to how to calculate inverse matrices, because the experience shows that many students just can't remember how to do it, even though it's quite an easy process. Okay, so this is the plan for today. And let's start out with the very first topic, which is Gaussian elimination. Gaussian elimination. Gaussian elimination. So I think that the best way to show you the example is just to go through examples. And I'm determined to show you quite a few examples. So it will take quite a long time, but what can you do? So the first example will be the system of linear equations, which looks like this. X plus 2y plus 2z is equal to 3. The second equation is 2x plus 2y minus 2z is equal to 0. And finally, 3x plus 4y is equal to 3. So this is our system of linear equations. But you know, you may notice that the number of variables is 3x, y, z, 3 variables. And the number of equations is also 3. You know, it's just accidental. It's just accidental. The beauty of Gaussian elimination that it can tackle any situation. You can have more equations than unknowns or vice versa. It doesn't matter. For Gaussian elimination, everything is fine. So Gaussian elimination is absolutely beautiful and reliable method. So let's start. What is your first step? What should you do to apply this method and to solve this problem, of course? First of all, you need to write down so-called augmented matrix of the system. Augmented matrix. What is this? Augmented matrix. Look at the system. So you can explicitly see that the first column is about x, about variable x. And these x's in the first column have coefficients 1, 2, 3. So this is going to be our first column as well. 1, 2, 3 in our matrix. So the second column is about y. Coefficients in front of y are 2, 2, 4. So this is our second column. And the third column will be 2 minus 2, 0. Why 0? Because there's no z here in the third row. But finally, we need to take into account these right-hand sides of these equations. 3, 0, 3. And this is our augmented matrix. This is our augmented matrix. If you don't write this column, it will be just a matrix of coefficients for a given system. But if you add this column, it will be called augmented matrix. And you know, the convention is to separate this column, the last column, from the rest by vertical bar. But it's not absolutely necessary. If you don't like it, you don't need to do it. Okay, so what next? What next? Now the next step is to bring this matrix to so-called row echelon form. It actually means that you need to get triangle of zeros here in this place. So, but how can we do it? How can we do it? What are the operations which are allowed? And of course, maybe you remember that there were operations called elementary operations over rows, only over rows in the metric. Remember about it. You are not allowed to operate with columns because it will cause too much confusion. That is why. So, what exactly are these 3 operations? So let me remind you, the first elementary operation was swapping the rows. You can easily swap any rows to put them in any order. You know why is it possible? The explanation is very easy, because every row corresponds to a separate equation. So for example, the first equation corresponds to the first row. Look at this, coefficients are the same. and so on. And that is why you realize that if you swap some equations inside this system, it won't change anything. It's just, it's very easy reasoning. Okay, so and the second elementary operation is that you are allowed to multiply the whole row by some non-zero constant. For example, if you're not happy with the numbers 1, 2, 2, 3, you can easily multiply them by 2, but minus 10 or so, Why is it possible? Again, let's look at the equation. If you multiply, for example, the first equation by some number, non-zero only, by 10, for example, what will change? Nothing will change. It will be the same equation, as you know from high school. So we already have two elementary operations. What is the third one? The third one sounds a little bit more complicated. This operation says that you can add one row, for example, the first row, multiplied by some non-zero constant to some other row. This sounds quite a fancy operation, but it's actually the most popular here in linear algebra. We are going to use it quite often, more often than others, I'm afraid. Okay, so now we are armed with these three operations, elementary operations over rows, not columns. I maintain this again. But what should be our goal to get zeros here? It's better to do it in two steps, So the first step will be about turning these guys into zero using only the first row. I'll explain it later. And the second step will be about getting rid of this guy, about turning it to zero. So you can easily bring this augmented matrix to row echelon form just in two steps. Okay, so let's start. And it's always to start off with this top left element. It should be 1. It's not a requirement, it's just very convenient to have 1 here. So, but we do have 1 already here. So let's start. It turns out that you don't need to change the first row, so we're just rewriting it. And now it's time to start performing our first step. So what can we do? To get rid of these 2 in the second row, you are allowed to use only the first row. So for example, you can multiply it by 2. It means that I'm going to multiply every single element of this row by -2 and add it to the second row and write the result on the second row. So let's start. 1 times -2 will be -2. -2 plus 2 will be 0. Again, 2 times -2 will give -4. -4 plus 2 will be -2. This element will turn into -4. -4 minus 2 will be -6. And finally, -6 plus 0 will be -6. So we are finished with the second row. Let's move to the next row. We still need to get rid of this guy, 3. And again, we are allowed to use only the first row. So let's multiply the elements of the first row by -3 this time, and add the result to the third row and write it down in the place of the third row. Okay, 1 times -3 will be -3. -3 plus 3 will be 0. The next element will turn into -6 after multiplication. -6 plus 2 will be -2. And this will be -6 plus 0 will be -6. And this will be -9 plus 3 -6 again. So we are finished with the first step. We achieved our goal. We did get zeros here. And at the same time, maybe you notice quite an interesting thing. The second and the third row are the same rows. They have the same elements. But I prefer to pretend to be a robot or computer or whatever you like. It's better to follow your algorithm without thinking too much about this beauty. Okay, so I'm rewriting the first row again. We are not going to change it. And now and the second row as well. Let it be rewritten. So how can we get rid of this guy? How can we turn it into 0? And the answer, and you are allowed to use only the previous row this time, because if you use the first row, you will this guy will turn into non-zero element at all. It will be like a vicious circle. So don't ever use the first row, only the previous row. But you see, the numbers are so nice. It's necessary to multiply the second row by -1 and add the result to the third row. You immediately get all zeros here. So we are done. So we did get zeros here. So this is called row echelon form of the matrix. So this was our second step. The first step was augmented matrix. The second step was row echelon form. What next? The next thing is to find so-called leading elements of each row. So we look at this matrix again, but now we are looking at one row at a time. We are sort of moving our eyes from the left to the right. And what are the leading elements? Leading element is the first non-zero element in this row if you look from the left to the right. But things are very easy with the first row because the very first element is already non-zero. So this is the leading element from the first row. Okay, let's move to the second row. The second row, this is this leading element. So we have two leading elements. Unfortunately, I forgot to simplify the second row. Let's do some more operation, one more operation. You can see quite ugly numbers in the second row. As for me, I'm tempted to divide them by -2 to get, as small numbers as possible. Let's do it. Let's do it. So the second row will be 0, 1, 3, 3, 0, 0, 0, 0. It will make things much simpler for us in the next step. So leading elements will be 1 here and 1 here. Okay, it was like not a very nice solution, but I think that you don't mind it. Okay, now after we have found leading elements, it's time to look again at this matrix, but this time in terms of columns, not rows. Do you remember that every column corresponded to some unknown? So the first column are coefficients in front of x, this coefficients about y, and this coefficients about z. And so what do we need to do next with this situation? We need to find column or columns without leading elements. You can immediately spot this column. This is the third column. It does not have any circled element, any leading elements which are circled. So that's what we are looking for. And the next step will be to realize. So this variable which corresponds to this column is called a free variable. So z is called free variable. Free variable. And by the way, the rest of the variables are called basic variables, but it doesn't matter so much. So what do we need to do with this free variable? We denote it as parameter t. In this problem, we have only one parameter, we have only one free variable. That is why we use only one letter t. But sometimes we can have two free variables. In this case, we use letters t1, t2, and so on. Okay, so what next? Now it's time to get back to the system of linear equations. As we noticed before, every row in this matrix corresponds to every equation. The first row hasn't changed, so it will be the same equation: x plus 2y plus 2z is equal to 3. But as for the second equation, you can see that it's changed a lot. So it will be y plus 3z is equal to 3. And the third equation just disappeared. It was redundant. It means that it was linearly dependent with others. But it doesn't matter. So what next in our algorithm? Now we just denoted z by t, so we can use this in our system. Let's substitute z with t. Plus 2t is equal to 3, y plus 3t is equal to 3. Okay. And now what next? As I said before, there are two types of variables. Z is a free variable, and the rest of the variables are called basic. So how to solve this system? The best idea is to leave these guys who are basic variables, x and y, on the left-hand side and move all the rest to the right-hand side. Okay, so the first equation will be rewritten like this, and the second equation will be like this. And it turns out that they already solved our problem. It's time to write out our answer. Our answer is the column of unknowns of our variables, and let's substitute our results instead of each of these. No, I haven't solved my problem. Sorry, too early, because I realized we already have y but not x yet. but it could be easily solved. Look at this. The first, from the first equation, we can get x is equal to 3 minus 2t, and we will move to I here. And then we can substitute this expression instead of y here. So, and let's simplify this. It will be minus 6 plus 6t. So these are like terms, of course. I'm sorry. It's sliding out of view, out of field of view. 4t minus 3. I hope I haven't made any mistakes. Hopefully. Okay, it doesn't matter after all. What matters that the order, the algorithm. Okay, so we have x here. Let's put it into frame. And now it's time to write our answer. So our answer, as I said before, will look like column of unknowns. And let's substitute our results. So the first result is x is 4t minus 3. Y was here. Y is 3 minus 3t. And finally, z was denoted by t. So this is actually the answer. But it's better to split it into the sum of columns. How can it be done? Look at this. So we pull out t and write here coefficients in front of t in every row. So for example, in the first row, you have 4t. It means the coefficient is 4. And that's it. So in the second row, you have minus 3. So it means that it has coefficient minus 3. And in the last row, t corresponds to 1. But you also have terms which are without t's. So for example, minus 3. Here it's just a number. 3 here and 0 here. So the convention is to write the solution of equation in this form. It's much more convenient for many reasons. Okay, so we are finished with the first example. It was like an introductory example. Now you know the algorithm, how to solve problems, to solve linear equations using this Gaussian elimination method. But you know what? Unfortunately, the situation could be, quite different. So, for example, in this problem 1, we had only one free variable. And many people get confused when they have to deal with two variables, with two free variables. That is why, let me give you another example. Another example, very similar system of equations. The number of unknowns is the same. These are the same guys, x, y, z. And the number of equations, let it be the same. 2x plus 2y plus 2z is equal to 2. And the last equation will be like 7x plus 7y plus 7z is equal to 7. Of course, you immediately see some patterns here, but my intention is to convince you that this algorithm is so good that it will always save you. You don't need to resolve this mysterious situation. Why does it look so beautiful? Maybe it means that I may need some shortcut. Of course, you will know everything about shortcuts later, but the first thing which you need to master is this algorithm. So let's pretend that we are just like robots. We don't know anything about the beauty of this system. Just apply our algorithm. So our first step, as usual, is to write down augmented matrix. Let's start out with this. So the first column will be 1, 2, 7, x's. The second column will be 1 to 7 again. Okay, no problem. We don't just pay attention to it. 1 to 7 again. And the right-hand sides are the same, 1 to 7. No worries at all. We need to perform our algorithm if we don't care about anything else. So our first goal, our first step is about zeroing out these guys. And the second step will be about turning this guy into 0, as usual, just as before. Okay, and to perform the first step, to get rid of these two guys, we are allowed to use only the first row. And we are lucky to have one here. So everything goes to plan. Okay, so let's rewrite the first row here. And now it's time to start dealing with the algorithm. So to get rid of 2 here, we need to multiply the first row by minus 2 and write the results here. Okay, minus 2 plus 2 will be 0. Minus 2 plus 2 will be 0 again. All the zeros. Look at this. Good. We don't mind it at all. What about 7 in the third row? This time we need to use the first row again, but multiplied by minus 7. Okay, minus 7 plus 7 will be 0. Minus 7 plus 7, again 0, 0, 0. So all of a sudden, all our process has finished earlier. we were prepared to perform the second step after that, but all of a sudden everything became 0. So it is a row echelon form, no problem at all. Okay, so what was our next step? Our next step was to find so-called leading elements of each row. There's nothing easier than this. Look at the first row. The very first element is leading element because it's not 0. And the other, the second and the third row, they don't have leading elements at all. So that's it. After that, we looked at the next step was to look at this matrix from another point of view, to look at the matrix in terms of columns. So again, every column corresponds to each unknown. So this column is about x's, this one is about y's, and this is about z. Okay. So and now we need to find column or columns which don't have leading elements. This time we have even 2 columns. Look at this. Second and the third column, they don't have leading elements at all. It means that this time our y and z are free variables. We have 2 variables compared to the previous case. Okay, and so we need to denote them. Let y be t1 and z be t2. And after that, we are allowed to get back to the system of equations, which is actually one equation only, because, as you can see, only one equation left, only on one row left. Okay, x plus y plus z is equal to 0. Very strange situation. We have only one equation, but it's quite normal. So now we need to substitute our notations. So y was denoted as t1 and z was denoted as t2. And after that, we realized that we have only one basic variable. So y and z were free variables and x is basic variable. And we usually try to leave basic variables in the left-hand side and move everything else to the right. So it looks like we finished with our task. And all is left to us is to write down the answer and to simplify it a little bit. Okay. So instead of x, we can write 1 minus t1 minus t2. Y was t1 and z was t2. And now it's time to split this column into the sum of simpler columns. Okay, so t1, let's have a look at the coefficients of t1. In the first row, you have minus t1. It means that coefficient is 1 minus 1. In the second row, just t1 corresponds to 1. And there's no t1 in the third row. It means that it has coefficient 0 there. Oh, sorry. It's sliding out of field of view. Plus t2, and the same procedure again. We have minus t2 here. It means minus 1, 0, and 1. And finally, we have a column without any t's. It will be 1, 0, 0. That's it. So as you can see, sometimes you have to deal with 2 free variables, or maybe even 3. It depends on the configuration of your system, linear system. So I hope that you will the picture is quite clear for you, but maybe you need maybe you are wondering what happens if you don't have free variables at all. Let's go from this example as well. So this is going to be our third example. Okay, so I have a linear system of equations for you here. X plus 2y plus 2z is equal to 3. 2x plus 2y minus 2z is equal to 1. 3x plus 4y minus z is equal to 3. Okay, this time maybe we will do things even quicker because we are getting more and more experienced now by the third example. Okay, so augmented matrix. The first column is 1, 2, 3. The second one, 2, 2, 4. The third one, 2 minus 2 minus 1. And right-hand side is 3, 1, 3. Okay. So we are happy again. We are lucky again, I thought. We have a 1 here. We don't need to worry about this guy. So this is going to be our first step, and this is going to be our second step, as usual. As usual for this situation. Okay, let's rewrite the first column. Or the first row, sorry. I'm rewriting. And now it's time to get rid of this 2. Of course, you know that we need to multiply the first row by minus 2. Okay, let's start. Minus 2 plus 2 will be 0. Minus 4 plus 2 will be minus 2. Minus 4 minus 2 will be minus 6. And minus 6 plus 1 will be minus 5. So we did get 0 here instead of 2. Now we need to get rid of 3 here. Again, we are going to use the first row, but this time we are going to multiply it by minus 3, and the result will be written down here. Okay, minus 3 plus 3 will be 0. Minus 6 plus 4 will be minus 2. Minus 6 minus 1 minus 7. And finally, minus 9 plus 6 will be minus 6. Our first goal has been achieved. We got zeros here. But now we need to get a 0 here instead of this element. And using the second row, it's very easy. You need just to multiply the second row by minus 1. And then add the result to the third row. It will be done. Okay. So let's rewrite the first row and the second row. Maybe it's a good idea to multiply the second row by minus 1, because these minuses look pretty annoying. So 0, 2, 6, 5 looks much better. And now it's time to get rid of these guys. So minus 2 by minus 1 will be 2. 2 plus minus 2 will be 0, of course. This 0 here. So 6 minus 7 will be minus 1. And finally, 5 minus 6 will be minus 1 as well. Okay. So we do have a row echelon form, because there is a triangle of zeros here. The next step is to find leading elements, but we can do it much quicker than last time. We have 3 leading elements for each row. And if we have a look at this matrix in terms of columns, it looks like we don't have columns without leading elements. Very confusing. Looks like something unusual. No, nothing unusual. No free variables. No free variables. It happens from time to time. No free variables. It's quite normal. Nothing out of order here. No free variables this time. What should we do next? We should just go to the next step. That's it. The next step was about getting back to the system of equations. So instead of rows, we are now going to write equations again. So the first row corresponds to equation x plus 2y plus 2z is equal to 3. The second row corresponds to equation 2y plus 6z is equal to 5. And finally, by the way, it would be a nice idea to multiply the third row by minus 1. Let's do it here. So it will look much better. So it will be z is equal to 1. And the recommendation as to how to solve this problem as efficient as possible is start with the bottom equation. In our case, it's been resolved already. We already get the variable f. Then move to the second equation and substitute z to this equation. So 2y plus 6 times 1 is equal to 5. And I'll go immediately to the next step. So we have z is equal to 1 here. Okay. And y would be equal to minus 1 divided by 2. And then after that, we can use this result in the first equation. So let's substitute it here. X plus 2 times minus 1 over 2 plus 2 is equal to 3. And what about the x? The x will be, I don't know, 2 probably. I'm not sure. I'm not even sure. Yeah, it looks like it's 2. X is equal to 2. So what happens now? It turns out that our solution is already been written. Let's just rewrite it in a conventional way. 2 minus 1/2 and 1. It means that there's no free variables, and at the same time it means that we have like a unique solution. We don't have any parameter t which always changes from minus infinity to plus infinity. That is why our solution is just unique. Only one solution for this system. So that's what it means when you don't have any free variables. Quite a normal situation. Nothing out of ordinary. Okay, so we already done 3 problems, 3 by 3. But maybe it would be a good idea to look at a very simple problem, just like for a break. Let's take a system 2 by 2, for example. 2x plus 4y. No, sorry, mistake. 2x plus y is equal to 3 will be my first equation. And the next one will be 4x plus 2y is equal to 6. Of course, maybe some of you might say that, oh, it's quite silly to solve such a simple problem by using a Gaussian elimination method. But nevertheless, I want to show it to you how to do it, just to give you the sense of how general all these methods are. Gaussian elimination can be applied to any system, even to the quite a small one. Let's do it. It won't take us a lot of time. So we are pretending that we didn't notice this nice thing, that the second equation actually is proportional to the first one, which means that this is actually the same equation. We can easily throw it out of our system. But I do it deliberately. I'm pretending that I didn't notice this so nice thing. I'm just going to apply my algorithm like a soulless robot. Okay. So let's write down augmented matrix as usual. 2, 4, 1, 2, and also this guy 3, 6. Gaussian elimination will look very, very simple in this case. Of course, we don't have 2 here, 1 here, but it doesn't matter because these two numbers, 2 and 4, are very nice. I forgot to mention that in this case, we have only one step to get row echelon form. Only this guy, only this element should be turned into 0, which is quite simple. Because the first row is very nice, we can multiply it by 2, the first row, and add the result to the second row, and we will be finished immediately. So let's rewrite the first row, 2, 1, 3. So minus 2 minus 2 will be minus 4 plus 4 will be 0, minus 2 plus 2, 0 again, and this is 0 again. So this is row echelon form. The next move is to find leading elements for each row. The first row does have a leading element, this one, and the second row doesn't. Let's see. After that, we remember that these columns correspond to each unknowns correspondingly, and so we are looking for the column or columns without leading elements. Okay, it's quite straightforward. This is the second column, which means that y is the pre-variable, and we denote it as t. After that, we get back to the system, to the equation, the first equation. 2x plus y is equal to 3. We substitute y with t. 2x plus t is equal to 3. And we express x. X is 3 minus 2, and x is equal to 3 over 2 minus 2 divided by 2. So this is our x. This time, something new is happening now. We will have to deal with fractions now. So I'm pretty happy that I decided to explain this example, because we haven't come across fractions before. And some people might get used as well when they bump into fractions. So everything is done for the better. Okay, so what was our next step? Our next step was just to write the answer. This time it will be column consisting of 2 components only. So x is equal 3 over 2 minus t over 2, and y was 2. And just as before, we need to split this guy into 2 columns. So t has coefficients minus 1/2, 1 here, and plus 3 divided by 2 and 0. But you know what? We always worry about this column, which is coefficients, which are coefficients in front of t. It's better to have integer numbers here. How to turn them into integers? It turns out that it's quite possible. Let's see how to do it. Let me explain you how to do it. I'm running out of paper. That is why I need to adjust my screen a little bit. Now it looks more or less fine. So it turns out that we need integer numbers here. That is why, how to do integer numbers? We can pull out minus 1 over 2. So it will be minus t over 2. And this will be 1 in this case, and this one will be multiplied by minus 2. So it looks better. But from here, it doesn't make sense to pull out anything. It won't get any better. Okay, so now this vector looks much better, but now we have a feeling that something strange, something untypical here. You know what? T is variable, and you can denote it by some other letter, by like, I don't know, capital T after all. In this case, it looks much nicer. But again, we are so used to the ordinary letter T, not the capital one. Why not denote it again, back like T? So it sounds like a trick, some trick. The explanation is very simple one. And the thing is that T, variable T, another method how to get answer in this beautiful form. I mean, especially about this column. So you can apply another reasoning to it. The thing is that T is a variable which can take arbitrary value from minus infinity to plus infinity. And if you divide this arbitrary value by -2, it won't change anything. This new value, which is T capital, will take the same values from minus infinity plus to infinity. That is why it's allowed to write T just instead of minus T over 2. But if this reasoning sounds a little bit abstract for you, just use this approach. So remember that it's better to get this column in front of T like integer numbers. It's much more convenient for our future tutorials. Okay, and now, you know, it's not the end of the first topic yet, because I haven't said anything about homogeneous systems or linear equations. Let's write it down. Homogeneous systems, homogeneous systems of linear equations. What are these guys? It turns out that so far we've been dealing with 4 problems, and they were all about non-homogeneous systems. What is the difference? Homogeneous system. So let me write down a very small homogeneous system. Okay, it consists of 2 equations. So maybe you immediately spotted the difference. If these right-hand sides are all zeros, in this case, it's called a homogeneous system, all zeros. If at least one of these elements, one of these numbers is non-zero, then it's called non-homogeneous. So far, we've been dealing only with non-homogeneous system. What is the difference as to how to solve them? It turns out that there's almost no difference. You can still apply this Gaussian elimination method and all algorithms, including leading elements, free variables, and all. The only difference is that you can, it's not necessary to write out the whole homogeneous matrix. Just a matrix of coefficients will be enough in this case. Because even if you write this column of zeros here, it won't change. It will never change. Whatever you do to the rows, it will never change. And that is why mathematicians are known to be quite lazy folk, and they prefer to write as less as possible. That is why, in case of homogeneous system, don't write this column to the right of zeros. It won't change anything. You will just be annoyed at having to write it all the time. Okay, let's solve this system, and just to compare the previous result with this result, just for educational purposes. We know that in case of two equations, we need to get rid only of this guy. Our algorithm consists of 1 step only, and numbers are very nice. We immediately see that it's enough to multiply the first row by -2 and add it to the second row, and will be finished. So it will be -6 plus 6, 0, -2 plus 2 will be 0. So we are finished. This is the row echelon form. And the only leading element here is 3 for the in the first row. And then if we look at the columns, we see that the second column is without leading elements. It means that y is a free variable again, just like in the previous case. Y is free. And that is why we denote it by letter T. And it's like a solution for variable y. After that, we are getting back to our equation. 3x plus y is equal to 0. Remember, we omitted this 0 column, but it's still 0. And after that, we can express x in terms of I. X is equal to -3, and which is equal to -t over 3. Okay. Oh, and now we can practice this trick. about getting rid of fractions, by the way. So our answer looks like a column, x and y. So let's substitute first our results. And t here. And of course, at the first move, we bring out t, and we are left with fraction here inside. -3. Oh, what is this? This is 1. This should be 1. And after that, we realize that we can actually easily multiply both components by -3, and nothing will change, just like last time. It will be 1, and this will be -3. Looks much neater. This answer, of course, looks much more beautiful than the previous one. The previous one was a little bit ugly. So there's almost no difference between homogeneous and non-homogeneous systems in terms of applying Gaussian elimination. The only difference is that it's not necessary to write this 0 column separated by a vertical bar. Absolutely necessary. Just remember that the right-hand side is always 0. So it looks like we finally finished with this Gaussian elimination. I hope you get the idea now of how to deal with these systems of linear equations. So it's now time to move to the second topic. Second topic is about linear dependence or independence of vectors. So let's write down the name of the topic: linear in, or maybe just dependence of vectors. How to explore this collection of vectors as to whether they are linear dependent or independent. But let me remind you the definition first from the last semester, from the previous semester, linear algebra. So we have collection of vectors E1, E2, and so on, and En. It could be any number of vectors with any number of components. It doesn't matter. So how to find out if they are dependent or independent? We need to build an equation. Look at this. So we take the first vector E1 and put coefficient x1 in front of it. So we'll get x1 times E1. Then the next vector gets coefficient x2 in front of it, E2, plus so on. And the same to the last term, xn times En. We need to set it equal to 0, not 0, but 0 vector. And we get this equation, very big equation. We need to solve it, then solve it. Solve this equation for these coefficients, for this unknown. Solve for x1 and so on, and xn. And so you get the result. And depending on this result, you may have two outcomes. The first outcome happens if all these guys, all these x's are equal to 0. So your answer will be these vectors E1, so on, En, are linearly independent. Independent. So this is going to be our first outcome. And in the opposite case, what is the opposite case? If at least one of these guys is non-zero, if at least one of these x1 and so on, x1 is not equal to 0, in this case, your answer will be dependent. These vectors are dependent or linearly dependent. I would like to know. So in theory, it looks very nice, very easy. But in practice, it looks like we'll have to deal with the system of linear equation. So let's go for the example. Let's go for one example. I took it from your tutorial sheet, but I don't remember the number. It was question 3, if I'm not mistaken. It doesn't matter so much, actually, but just, for order. Okay, in this question, you are given 3 vectors. The first vector E1 is 1, 1, 0. The second one is 1, 0, 1. Very ugly writing, I don't know why. And the third vector is 0, 1, 1. Okay. And you are asked to explore, to find out if they are linearly dependent or independent. So how can we do it? We can do it according to the process method described just earlier. So we need to build this equation in the first place. So x1 e1 plus x2 e2 plus x3 e3, and it's all equal to zero vector. Okay. So and now we need to solve this equation. How can it be done? Let's use our intuition. We have components of each vector, and I think it might be a good idea to substitute this vector by this column of this component. Let's just do it. X1 gets multiplied by column 1, 1, 0 instead of E1. The same goes here instead of vector E2, 1, 0, 1, plus X3 times the third vector, which is 0, 1, 1, and it's all equal to 0, 0, 0 column. So now it looks even more daunting probably for some. But you know what? Look at this first term, for example. What is this column? It's matrix. And matrix gets multiplied by constant x1. This is a very well-known operation. It means that we can multiply every element of this matrix by x1. So this whole term turns into the column x1, x1, 0. So we are just performing very well-known matrix operation. So we can do the same to the second column, second term. x2, 0, x2. And the third column will turn into, the third term, sorry, will turn into the column 0, x3, x3. And finally, it's all equal to 0, 0 column. And now, inspired, we immediately realize that it's another matrix operation here. Three matrices of the same size are being added together. We know how to perform this operation. You need to add up together corresponding elements. So x1 plus x2 plus 0 will give you x1 plus x2, the first element. Then the second row will give you x1 plus 0 plus x3, which is just x1 plus x3. And similarly, the last element will be x2 plus x3, and it's all equal to 0, 0, 0. Okay. And finally, we have a matrix equation, matrix equality. This is very well-known definition as well. Two matrices are equal to each other if and only if the corresponding elements are equal to each other. What are corresponding elements in our case? So this guy here corresponds to this one. So they need to be equal. Okay, we get the first equation, by the way. The second equation is x1 plus x3 is equal to 0 again. And finally, x2 plus x3 is equal to 0. So we ended up having typical classical system of linear equations. And now we know how to solve. This is homogeneous equation, by the way. Look at these zeros, but it doesn't matter so much. And now we need to solve this equation. But now this is going to be like the fifth linear system during this tutorial. Okay, let's write down the matrix of coefficients. We don't need even augmented matrix this time. And let's start. So the first, sorry, it should be in the field of U, first of all. So the first equation corresponds to row 1, 1, 0, because the third variable x3 is missing here. That is why it has coefficient 0. Okay, in the second equation, x2 is missing. That is why it will be 1, 0, 1. 1, 0, 1. And the third row, the third equation, has x1 missing. That is why it will be 0, 1, 1. 0, 1, 1. And it's not necessary to write the third column of zeros, as I said before. Okay, we can use a Gaussian elimination now, the most reliable method, as you already aware of. So we need to get rid of these guys during the first step and to get rid of this guy during the second step, as usual. Okay, how to get rid of the first guy? I need to rewrite the first row first. And then we can multiply the first row by -1 and add it to the second row. So what we will get? -1 plus 1 will be 0, -1 plus 0, -1, and this will be 1. And we are quite lucky with this particular problem because we already have 0 here. So this is the end of step 1. Okay, the second step will be about eliminating this guy using the previous row. But you know, the numbers are just wonderful. Everything is so convenient in this task. We don't need to worry about too much about arithmetics. Okay, so the first 2 rows are ready. By the way, it's better to multiply the second row by -1. It will look much better. When the leading element is non-negative, it's always better, much more convenient. Okay, and now to turn this guy to 0, we need to add the third row to the second row. It will be 0, 0, and 2. Okay. The next thing is to find leading elements, which are 1. For the second row, it's 2. For the third row, it's 2. We already seen this situation before. No free variables at all. No columns without leading elements. Okay, we know, we are quite familiar with the situation. Nothing unusual about it. We just move further. So now it's time to get back to our equations. So the first row corresponds to x plus y is equal to 0. The second row is y minus z is equal to 0. And the third row, I forgot to divide this third row by 2. Let's divide it. It will be 1. As you can see, the equation is much more better immediately. 0, 0, 0, sorry. It's a mistake. So, and now we are going to solve this problem, moving from the very bottom, the very last equation, to the second and then to the first. So last equation has already been solved. We got z is equal to 0. If we use this z equal to 0 in the second equation, we immediately get that y is equal to 0 as well. And then, substituting these results to the first equation, we get that x is 0 as well. So the system has been solved. It has unique solution, 0 solution. What does it mean? Let's look at our diagram. So let's look at our previous diagram. What do we have here? We have this case. All our unknowns, all our coefficients are 0. That is why our answer is independent. So the answer to this problem is that our vectors E1, E2, E3 are linearly independent. Independent. So that's it. So this is a classical method using the definition of linearly dependent on dependent vectors. But some of you maybe already know that there is a shortcut, actually. It's a very nice shortcut because it looks like my solution is so long, so troublesome. So what is the shortcut? And can it be used in this situation? The thing is, shortcuts are always so wonderful, so easy compared to this general way of solving. But the sad news about them that they are not universal. They are not universal. But let's discuss it anyway. Maybe you may come across this unique, nice situation. You would like to use shortcut. Okay, shortcut. So the question is there a better way of determining if the vectors are dependent or independent? The answer is yes, only if the matrix is square. So if your matrix A, this is a matrix of coefficients, matrix, in parentheses, matrix of coefficients for your system, coefficients. If that matrix A is square, what does it mean? It means that it has a dimension 2 by 2, 3 by 3, 4 by 4, and so. In this case, it's possible to calculate determinant of this matrix. So find determinant of this matrix, determinant of A, and what next? And next, your answer will depend on this determinant. So if determinant of A is non-zero, your answer will be independent. These vectors are independent. And in the opposite case, if determinant is equal to 0, the answer will be dependent. So I'm talking about the system of linear equations. So I assume that we already build up this equation. No, I forgot to mention that how to build this matrix. Okay, let's go through the example. Let's get back to our example, by the way. Example, the same question 3, by the way. Example, it's always better to show things on example. Example, the same question 3. We have 3 vectors there, E1, E2, and E3. You can put them in columns or in rows, it doesn't matter. So let's put them in rows. So 1, 1, 0. Do you remember it was our vector E1. E2 was 1, 0, 1. And this 1, 0, 0, 1, 1. So this will be your matrix A. So matrix A consists of columns of your coordinates of your vectors, and that's it. Then you calculate the determinant of this matrix. It should be non-zero, of course. It should be non-zero. You can check it. And if the determinant is non-zero, then your answer will be independent. Of course, this is a nice shortcut, very nice, of course, nothing compared to my algorithm. But you know what? They said the bad news is that it's not universal. Only if there is an amazing coincidence that matrix is square, then you can apply this method. Of course, it's much shorter, it's less time consuming. But if you're dealing with the case when the number of equations is, for example, 7, and number of unknowns is 3, that is the dimension of the matrix is 3 by 7, you can't apply this method, because just determinant exists only for square matrices. So as everything has limitations. Everything has limitations. Okay, so I finished with this topic. And finally, the third topic is a very simple one, but I need to go through it. How to find inverse of matrices. Many people, many students just feel confused about it, because even though it's very easy, but it can be really confusing. So let's go through like two examples. I'm determined to finish the first one because it will be about matrix 2 by 2, and maybe maybe I'll leave it to for homework the second example, which will be about 3 by 3. So let's start with some matrix which is 2 by 2, 1, 2, 3, 4, for example. So what is the algorithm? So the first step, you need to find determinant of matrix A. Determinant looks like 1, 2, 3, 4. You know how to calculate determinants. 1 times 4 minus 3 times 4 will give us minus 2. And you know, the first step is actually crucial. Only if the determinant is non-zero, you can proceed with your algorithm. Otherwise, if it's equal to 0, it means that the inverse doesn't exist. And this will be the end to the problem. But of course, no one is so lucky, especially during exams, to get this case. So in most of the cases, in any case, you will get this result. Okay, so the next step is to compile so-called matrix of cofactors. Let's denote it like A star. How to get this matrix? It means that instead of each element in the initial matrix, you need to write its cofactor. How to do it? Let's prepare first the associated matrix of signs. These are signs for every position. Now we are going to use this matrix. Okay, so how to get cofactor? Let's start with this element, which is in the top left corner. To calculate this cofactor, you need to cross out the row and the column in which this element is positioned. So let me use my pen. So 1 is positioned, this element, in the first row. Let's cross it out, and the first column. You are left with 4. So, but let's write down 4 here. But then you need to look out the position matrix. Position sign says +1. It means that multiply your result after crossing out by +1. But multiplication by +1 doesn't change anything. So it's still 4. So we are done with the first element. Let's move to the second one, 2. 2 is in the same row, but in the second column. We need to cross out this row and this column, and we are left with 3. But the position matrix says that multiply the result by -1 this time. This means that 3 multiplied by -1 will give us -3. So the sign should be changed, should be negative this time. Okay, and so on. So 3 is in the second row and the first column, so we cross them out, and we are left with 2. Position says multiply by minus. It will be -2 as a result. And finally, the last result will be just 1. So this is the matrix of cofactors. We replaced every element in the initial matrix A by its cofactor. Cofactors take into account these signs. Okay, the third step is very easy. We need to transpose this matrix. So A star transposed. Transposition is very, very easy operation. How should it be done? The first column was 4 minus 2, and it becomes the first row, 4 minus 2. And similarly, the second column was -3, 1, but now it becomes the second row, sorry. And the final step is writing down the inverse of matrix A minus 1. This is a formula, very famous formula. 1 divided by determinant of A times the matrix obtained in the previous step, which is R star transposed. And now we can substitute with our results. So determinant was -2, so 1 divided by -2, and this is the matrix we obtained in step 3. Okay, so we are done. It's always, of course, you can actually divide every element by -2, but I feel it's sort of lazy to do it because it looks much neater without fractions. Otherwise, you might get fractions here. So that's it. But I would add the 5th steps here. Actually, it's always a good idea to check your result. How can we check that we haven't made any mistakes? So we need to multiply A minus 1 by 1. Or by matrix A, if we are supposed to get what is it called? Identical matrix. Or you can do it in reverse order. You can multiply A by A minus 1, and you will get the identity matrix. But I'm not going to do this because hopefully you know how to do multiplication. You can practice at home. So especially during exams, it's quite a good idea to check your result immediately because this process can be quite complicated, especially for the matrix 3 by 3. That is why if you feel that you still have a lot of time, so I would recommend you to do this. This will give you a very nice feeling that, at least this task has been solved correctly. Okay, and the last problem, I'm not going to finish it because it's going to be too much, but at least I want to start doing this task. So how about finding the reverse matrix to a matrix 3 by 3? Let's take some matrix. I can't find any matrix, by the way. I hadn't prepared for this. So where is it? I can see something here in my notebooks, so probably this matrix. I'm not sure that it has determinant non-zero. Okay, so let's start dealing with this matrix. So 2, 0, 1, -1, 4, -1, 1, 2, 0. Okay, so I'm not going to go through the whole algorithm all over again. I think that you can easily do it at home. What I'm going to do now, I just want to show you how to compile this matrix of cofactors, because sometimes it can be tricky, especially in this case. So let's start doing this matrix as A star, and I need a lot of space here probably. I need to write out this matrix of signs: plus, minus, plus, minus, plus, minus, plus, minus, plus. So it will be very handy to have this matrix here. Okay, let's start dealing with cofactors. So let's start with the very first element, 2. It's located in the first row and the first column. And we are left with the matrix this time. Unlike in the previous example, what do we need to do? We need to calculate the determinant of this matrix. It's better to do it in your mind, to be honest, because there will be too much writing. I don't think it's a very challenging task for you. So 4 times 0 will be 4. Plus minus 2 will be, what am I saying? 4 times 0 will be 0, of course. So 0 plus 2 will be 2. And position says just this result is true. So we got 2. So cofactor of element 2 is 2 as well. It's just a coincidence. Okay, let's move to this 0 element. This time we are crossing out the first row again, but the second column. And now we need to calculate this determinant. This determinant will be this times this will be 0. 0 minus minus 1 will be 1. But the positions say multiply the result by minus 1. So it will give us minus 1. Minus 1. So the cofactor of 0 will be minus 1. Let's do one more element, and maybe it will be enough. So we got this element 1. So cross out its position, and determinant will be minus 2 minus 4, which will be minus 6, and plus nothing, minus 6. Minus 6. So the third element is minus 6. Let's do one more element from the second row, this minus 1. So cross out the second row and the first column, and the determinant will be 0 times 0. I need to have a third hand to point you out, but you can easily see it. 0 by 0 minus 2 times 1. It will be minus 2, but the position said it will be minus 2 by minus 2. So it will be plus 2, and so on, and so on. So it does require some concentration, but it's not difficult at all. It's not something about calculus or something like this. So that's it for today. So this was like an introductory tutorial, revision of the material studied above. And as you already know, we do need this Gaussian elimination quite extensively in almost every tutorial. So I hope it was of some help to you. Okay, that's it.